Imagine you're reading the sentence, "The riverbank was steep." Your brain instantly understands that bank refers to the edge of a river, not a financial institution. Humans naturally use context to interpret meaning. For a large language model, however, this understanding must be learned. The model looks at surrounding words like river and steep to determine what bank means in this specific sentence. It combines these signals to create a context-aware representation of the word. This is known as contextual embedding, where a word's meaning is shaped by the words around it rather than being fixed. Each word gathers information from its neighbors, allowing the model to capture subtle differences in meaning. This process is powered by the attention mechanism in transformers, where each word evaluates how much other words influence it. In this video, we'll explore how this works step by step and see how models transform simple words into rich, context-driven meanings.
All right, let's build on what we learned in the previous video. Take a simple word like apple. The first step is to convert this word into a numerical form using tokenization and the embedding layer. This gives us a vector, a list of numbers that represents the word in a way a model can understand.
So hey everyone, till now we know how we can convert a text into a token. So till now we have a text, we apply the input embedding on it, we apply the token embedding on it, and we add a positional embedding to the token, and then as the data flows, it flows through a layer normalization layer which normalize the token. Okay, so we convert the token between 0 and 1 values. That's what normalization is. So we complete this normalization and we reach. So today we are going to discuss, this is the main topic of this video. Today we are going to discuss about these query, key and value weights. This normalized token flows through these weights, and we matrix multiply the token with these weights, and then we get our query, key and value vectors. So how do we do this? Let's go ahead and check. If you're still confused about how did we get these query, key and value weights, so these are trained by the model. So these are learned by the model over a period of time using a gradient descent and backpropagation. If you don't know about this, you can watch my video on backpropagation and how the weights are learned in a model. So yeah, we do matrix multiplication and we get query key value vectors, and we apply attention on them and we get a contextual embedding. So let's go back to the animation and check it complete.
So as you saw in the 3D architecture of a transformer, we have three important components: query, key, and value. Now let's take our word embedding vector and pass it through these three sets of weights. What we're essentially doing here is in matrix multiplication, multiplying rows by columns and summing the results. It may sound complex, but at its core, it's just straightforward matrix math. By doing this, we transform our original embedding into three new vectors: the query vector, the key vector, and the value vector. Now pause for a moment, because this is a crucial step. Before we move forward, let's take a step back and really understand what these three vectors actually represent and why transformers need all three of them. The philosophy behind query, key, and value vectors is inspired by how humans selectively pay attention in conversations. Instead of treating all words equally, each word actively asks, "What information do I need?" Query, while other words respond with This is what I represent key. If there is a strong match, the actual information value is shared. This creates a dynamic information exchange where meaning is not fixed but constructed through relationships. In essence, attention is like a soft lookup system where relevance determines influence, allowing each word to gather only the most useful context and form a deeper situation-aware understanding. All right, now let's start what I like to call the matching game. Take the sentence, Apple likes juice. Our goal here is to encode the context of likes and juice into the word apple. Just like we did before, we first convert each word into its query, key, and value vectors using the learned weight matrices. Now comes the interesting part. We take the key matrix and transpose it and then multiply it with the query matrix. This gives us what are called raw attention scores. Think of these scores as measuring how much does one word care about another word. And if we look at our example, we start to notice something powerful. Both Apple and likes assign higher attention to the word juice. This means the model is already beginning to understand that juice plays an important role in defining the context of the sentence. But these are still raw scores. In the next step, we'll refine them to make this attention more meaningful and stable.
So before we go further ahead, I would like to explain you a concept of softmax scaling and how does that work. So how softmax works. The basic idea of softmax scaling is to get an output between 0 and 1. So we are just trying to compress all the data points in the range of 0 to 1. So if we go further, for example, we have these vectors apple, likes, and juice. We take the exponential of each data point. So we take the exponential of apple, likes, and juice data points. Next step is to sum all these data points exponentials, which is 3.063 for this example. Next, we divide each element's data points exponential by the sum of all the exponentials. And this is how we get our values in the range of 0 and 1. You can also show it in the terms of a percentage. For example, the attention paid from apple to apple is just 34.2%, and the attention paid from likes from apple to likes is 30.3%, and attention from apple to juice is 35.5%. So we can take them as we just take them as percentage. We compress the data points from 0 to 1. That's what the objective of softmax scaling is. Let's move ahead and complete our attention scores. So softmax in a nutshell: take the scale scores, raise power for each score, sum all exponentials, and divide each by the sum.
All right, now we have our raw attention scores, but they're not quite ready to use yet. We need to refine them into something more stable and meaningful. So here's what we do. First, we scale the attention scores by dividing each value by the square root of the key vector's dimension. This step helps prevent the values from becoming too large, which could make learning unstable. Once we've scaled the scores, we move to the next step. We apply the softmax function.
Okay, let's pause for a moment and try to understand how does softmax function works. So, if we look at the formula, we take exponential of our target term and divide it by sum of all exponentials. Step 1 is to raise exponential to the power of each score. Step 2 is to sum these values. We will use this sum as denominator. Then we divide each exponential by the sum giving us our final percentages. As we know, all percentage should add to 100. Next step, if we visualize it using a bar graph, we can see how each word pays attention to other words. Attention from apple to apple is 34.5%, and apple to likes is 30.3%, and highest attention paid by apple is to juice 35.5%.
Row by row, what does Softmax do? It converts these scores into probabilities values between 0 and 1 that all add up to 1. These are our final attention weights. Now, instead of just raw comparisons, we have a clear distribution that tells us exactly how much each word should focus on the others.
Now we've reached the final and most important step, creating the contextual embedding. Up until now, we've calculated our attention weights, but we haven't actually used them yet. This is where everything comes together. We take these attention weights and multiply them with the value matrix that we created earlier. What does this mean? Each attention weight determines how much importance we give to each word's value vector. We perform a weighted combination, essentially blending information from all the words based on their importance. So for the word apple, its new representation is no longer just about apple alone. Instead, it becomes a mix of information from likes and juice, weighted by how relevant those words are. And the result? We get a contextual output vector. This means the embedding form apple now carries awareness of the entire sentence. It understands that in this context, apple is related to liking juice. And that's the magic of attention, turning simple word vectors into rich, context-aware representations.
Okay, so finally now we can say that we have perfectly contextually embedded a vector. What does that mean? It means the context of apple is finally encoded in the token of juice, and the context of likes is also embedded in the token of juice. In simpler terms, we can now say that juice knows that likes and apple also matter in this sentence, which will help us to predict the next token. So to sum it all up, in today's video, we understood how we basically apply attention and how we use our query key value matrices to create query key value vectors, which then we use for attention matrix Softmax and to create attention and contextual embeddings. So this is enough for this video. In the next video, we are going to talk about the masked attention, and which you can just maybe see here. Yeah, this one. So you can see the masked attention applied in LLM. We are going to understand that in the next video. Thanks for your time. If you like this video, please like and subscribe. Thanks for your time. Goodbye.